half equation method. So redox reactions are actually at the crux of these two, redox reactions are what we need to continue talking about. Now there are two electrochemical cells. There are voltaic cells. If next to voltaic cells, if you want to put the word battery, you can, because that's what I think of. It's like a chemical battery. And I'll show you what this looks like, but basically what your battery does is provide, well, you provide the path as you put your battery into a device, but basically a flow of electrons, okay, associated with a redox reaction. That's how batteries work. If you've ever, the bottom one, way back when in Chem 1, we talked about the electrolysis of water, and I kind of showed you a picture. Basically, if you take H2O and you run a current through it, okay, you can make it break down into the hydrogen and oxygen gas. Now, just for kicks, let's go ahead and confirm that that's a redox reaction. You guys would probably tell me, and I'm going to tell you that oxygen's behaving correctly over here. So it's an oxidation number of -2. Both of those hydrogens are an oxidation number of +1. What's the oxidation number for the hydrogen atoms in H2? 0. Yep. How about the oxygen atoms in O2? Also 0. So, I mean, I just think this is just adorable. Do you see where the hydrogens are being, what, reduced? Okay, and oxygen is being oxidized. It's increasing its oxidation number. So anyway, that's an example of a redox reaction that's occurring, being driven by electricity. Okay, but like I said, this one up here, it works. You have a redox reaction that is actually creating electricity, the flow of electrons. It's a wonderful thing. And we are going to focus more on voltaic cells, the whole battery thing, rather than the electrolytic cells. Part 6 is all about electrolytic cells, and we aren't going to do that. So this is going to be kind of focusing on voltaic cells that create electricity. So the anatomy of a battery, the anatomy of an electrochemical cell looks like this. You need to have a chamber or a post that is what we call the anode. Now, the way I remember anode is the whole vowel thing. So we talked about oxidation reduction. Of course, O is a vowel, A is a vowel. So oxidation occurs at the anode. And remember what oxidation is. It's basically the increase of oxidation number, and it increases by giving up electrons. Okay, so electrons are released. Okay, the other or another part of the cell is the cathode. So cathode starts with a vowel, and so it must be associated with reduction. R is a vowel too. Sorry, vowel. Consonant. Like, oh my gosh. A cathode starts with a consonant, and so it actually is associated with the reduction. So an atom is reduced as it gains electrons, so this is where electrons are consumed. So your cell also needs something to connect the cathode and the anode, and that's your external circuit. And think of this actually in the case of if you're using a battery to power something, this is the something that you're powering. Okay, that's your external circuit connecting the anode and the cathode. And then it needs, if it doesn't have a salt bridge, it will quickly die out. Salt bridge is kind of a subtle thing, and I'll show you a diagram here in a minute. But with the anode, with the anode giving up electrons, it's going to become deficient. It's going to become, giving up electrons, it's going to be negatively charged. So it needs something to, positively charged. It needs something to kind of compensate for the negative charge it's losing. So the salt bridge is kind of a subtle sort of migration of charges between the two chambers, compartments. So here is a diagram of an electrochemical cell. And I can't show you that, can't show you this. Looks like a battery. But I can show you this. Okay? So let's see if we can find the anode where oxidation is occurring and the cathode where reduction is occurring. So this is actually, oops, let me pick a different color. Okay, this is the anode. Can you see how I know it's the anode? Because actually we have electrons are leaving the scene. Okay, electrons are being generated. Okay, so oxidation is occurring here. Anode oxidation. We have a path for the electrons to flow through. This can be a wire, okay? Wires are great. It can be your gizmo, where electrons are flowing through to power it. But if this is your external circuit, I can't spell circuit, okay? And then over here, this must be your cathode. And it kind of makes sense, because doesn't it look like electrons are being consumed over here? So this is where your reduction is going to occur. Okay, I mentioned kind of the salt bridge is like a migration of charges. There's your salt bridge kind of dipping into both chambers like that. So in this case, we actually have copper that's being oxidized, and we have silver that's being reduced. So this down here, and we'll be talking about this, this is the overall chemistry of what's going on in both of those cells collectively. Copper is being oxidized, okay, going from what, a 0 to a +2, and silver is being reduced, going from a +1 to a 0. This is exactly what we've been talking about. So one of the things we need to be able to do with these cells, electrochemical cells, is to break them down into their two half reactions, kind of like we were just doing. So the copper, actually, as 1 mole of copper will give up 2 moles of electrons, okay? Then if 2 moles of electrons are given up, then actually 2 moles of electrons need to be consumed by the silver. So that's why we scaled up this other half reaction. 2 moles of the silver ion will require 2 moles of electrons to form 2 moles of silver solid at the 0 oxidation state. So again, just like we did a minute ago in adding our 2 half reactions, those are going to be balanced for both charge and mass. We go ahead and our electrons cancel. We have 1 mole of copper solid reacts with 2 moles of silver to form 1 mole of the copper 2 plus 2 and 2 moles of the silver solid at a 0 oxidation state. So you're going to want to know how to write these cells shorthand. So you always start with the anode, and then you do a double bar, and then you do the cathode. So anode, double bar, cathode. You have a single bar, like I guess it'd be a vertical bar. You have a single vertical bar between what's being in the anode. Since we're talking about oxidation, we go ahead and go from left to right, write what's being oxidized. Copper is being oxidized from 0 to +2. Double bar means we're entering the other component or compartment or chamber, and then we begin with what's reduced. The silver +1 is reduced to silver 0. So that's it. That's kind of shorthand notation. So why do electrons flow? And it kind of reminds me of kind of pressure gradients. Anytime there's a gradient just means from location A to location B, there's excess at A and there's a deficient at B. So basically, as electrons are released at the anode, it creates an excess of electrons, and then they flow to where there's a deficient of electrons at the cathode. And that actually flow of electrons from where there's excess to where it's deficient is what's called the electromotive force, and it's measured in units of volts. So on the previous cell that we looked at, you guys can look back if you want to, but on the one cell that we looked at, there was like a voltmeter there for the external circuit, okay? And so that voltmeter was measuring what we saw, the cell potential, the difference in electrons from one side to the other. So a volt is a measure of energy per charge, joules per coulombs. Don't have to know too much about this. We'll be just dealing with volts. But just to kind of tell you what a coulomb is with regard to charge, coulomb is the charge on a single electron, a cute little coulomb, okay, oh, excuse me, cute little electron, has a charge of 1.6022 times 10 to the minus 19th. If you take that times Avogadro's number, you see that actually a mole of electrons has a charge of, and I did that yesterday, the geek that I am, has a mole of electrons has a charge of 9.65 times 10 to the 4th coulombs. So anyway, okay, so we're going to use volts to talk about what we call the cell potentials, the voltage that you can get from an anode and a cathode, the chemistry that's happening in an anode and cathode. So we have these little knot things, standard cell potentials. That little knot thing is the same thing we've been talking about, that standard temperature of 25 degrees Celsius, a pressure of 1 atmosphere. If we're dealing with any sort of aqueous solutions, the concentration of the solutions will be 1 molar. And the units for E are going to be in units of volts. Standard cell potentials. Ooh, Gibbs free energy. Oh my goodness. Gibbs free energy of a reaction. That's the exact same Gibbs free energy we've been talking about. Gibbs free energy is equal to negative N. N is the mole of electrons that are flowing. F is a constant, Faraday's constant. And E0 is the potential of that cell with that particular set of anode and cathode chambers. So E0 is the standard cell potential. And I don't know if you were here, Hunter, I don't think you were, but I gave you the other day for your final exam what your equation sheet will look like, and I think I give you Faraday's constant there too. Almost sounds like a movie, Faraday's constant. So Gibbs free energy of a redox reaction is equal to the negative number of electrons that will flow, moles of electrons flowing, Faraday's constant, times the cell potential. So this is good. This is all consistent. We said that as written from left to right, your reaction will proceed. It will be what we say spontaneous from left to right. If the Gibbs free energy of the reaction, change in Gibbs free energy of the reaction, is negative. So we're going to be looking at cell potentials that are positive and negatives. So your cell potentials can be positive or negative. But I hope this makes sense. If you need delta G to be negative to be spontaneous, then that means that in this relationship, you need your cell potential to be positive to be spontaneous. So your cell potentials need to be positive, greater than 0, in order for it to be spontaneous. That fits right in with what else we were talking about. Standard cell potentials. So this is the E0, standard cell potentials. So there are tables of standard cell potentials, and they are what we call just half cell potentials. Specifically, they are for reduction. I don't know why they picked reduction. I guess there's a reason. Okay. So here you go. There are, I think I have 3 or 4 slides. The first several slides are all half reactions occurring in acidic conditions. So there at the there at the right, far right, these are what we call your half cell potentials. And I'm going to put a little RED there. This right here really probably should say E not RED. Why? Because they're all reduction half cell potentials. How do I know the reduction? Well, check this out. Okay. Notice that we're adding electrons, okay, and something's being reduced. Fluorine's a good example. Fluorine's going from a what? A 0 to a -1. Okay? They're all reduction half cells, potentials. So that's the first page. Now the other thing, as I scroll through these, usually I don't really scroll through, there's only a few pages, but now this is pretty important. Watch this. Now as I scroll through them, look at the trend. These are not arranged alphabetically. These have the highest on purpose. These have the highest on the first page, and they get smaller. There's that first page. There's the next page. These are all half cell reduction potentials. Okay, and check out, look at this. Actually, this guy right here, I'm going to go ahead, if your notes, if you want to put an S period H period E, you can. Okay, that's the standard hydrogen electrode. So here they start to get negative. What do we say if you have a negative cell potential? Oh my gosh, if it's negative, negative times negative in that thing I just showed you a minute ago makes your Gibbs free energy positive, and that would not be spontaneous. So we're going to talk about that. Then I end up just, Peter, with a few half cell reduction potentials in basic solution. All right. Well, let's make some sense of this. Well, okay. So yeah, the tables I showed you went from the highest E0 to the lowest E0, including negative E0s. So what you're going to see is that when you go to your closet to pull out two things, you know, something that's for a redox reaction, you have to have reduction and oxidation. What you're going to do for the reduction half is pick out the highest reduction, okay? And then for the oxidation one, you're going to pick out the lowest reduction, and I'll just show you how this works here in a minute. Basically swing it around the reaction arrow and make it oxidation and change the sign of the E0. I'll show you what that looks like. So just kind of focusing on these are a subset of what you saw on the tables. Okay, this is just a subset of what you saw. They are arranged from the highest half reduction reaction to the lowest. Okay, so the point on this slide is as you go up, you get a stronger and stronger. Those make great reduction half cells. Okay, as you go down, they make the strongest oxidation half cells. Because, like I said, and it's easiest to kind of show you, for the thing to use this table for something that's being oxidized, what you're going to see us do basically is pivot around the reaction arrow and change the sign of the E0 half cell potential. Okay, so yep. So like I said, what I would do at the top of those columns on for that data, I think that might be in Appendix D, I'm not sure, is put RED as a little subscript under the E0. Okay. So now, we are going to have to, here in a minute, we got to know what the potential for the half cell, for the oxidation half cell potential is. We do need to know the oxidation, the potential. Okay. So we're going to have to swing it around the reaction arrow and change its sign. So this is an important one. Those values, those cell potentials, actually are intensive properties of the cell. They do not depend upon amount. okay? So we are going to have to scale up like you saw with silver a minute ago, scale up the half reaction, like we had to go to 2 Ag goes to form 2 Ag plus 2 electrons. We're going to do that, but the E0 will not be scaled up, okay? It's constant. I'm going to spend a minute to talk about that. Remember I told you a minute ago to put the SHE there for the hydrogen thing? Okay, actually, when you look at tables, they are compared against using the redox reaction for hydrogen. And I'll show you what that looks like. It's basically calculated against a standard hydrogen electrode. I guess I'm going to show you that now. So, standard hydrogen electrode, the SHE, that was the one I told you to circle. Okay? Notice that that's the reduction potential. The oxidation potential is also 0, but it's going the other way. This is going from a 0 to a +1 oxidation. This is what the SHE, I want to say she-devil, this is what the SHE looks like. Okay? It gives you, platinum actually, instead of, provides the surface for hydrogen gas that's bubbled in over the platinum to go ahead and be oxidized. In the solution, we have the hydrogen cation to go ahead and be reduced. So that is what is one of your cells. And then you match that cell up with something else. So I've got 2 examples here. So this is actually showing you measuring copper, and this is measuring zinc. If you go back a few slides ago and you look at the potential for copper being reduced, you're going to see a plus 0.340. If you go back and look at zinc being reduced, you're going to see a negative 0.763 on that table. So that's where these values come from. That's important to know, but what's really important to know here in a minute is how do you come up with the cell potential, not if it has a SHE as part of it, but what if, I'll show an example. So this is the chemistry that's going on for what you saw a minute ago with the copper being reduced. This is a little bit extra where we have the standard hydrogen electrode because now we have to show the PT, that's platinum surface for the oxidation reduction to happen. And this is shorthand notation for the zinc. Okay. So this is kind of getting to where I wanted to get to today. So let's look at some redox reactions, a couple cells, an anode, a cathode, and what sort of cell potential we can have. So again, the tables will give you half cell potentials for the redox reaction, but we're going to need them for the oxidation reaction too. So we are going to go look at this example where we said the copper was being releasing electrons, that's oxidation. So we said that that's happening at the anode. And then we said that the silver is being reduced, happening at the cathode. So if we look up on that table, you're going to find the potential for the reduction, you're going to find the potential for the reduction of copper is plus 0.340. So if it's being oxidized, it's minus 0.430. For the half cell potential for the silver, you're going to find it is plus 0.800. So that's the chemistry we have going on in this particular cell. So simply, the overall potential of the cell, we add up the two half cells, round to 3 decimals, and you get plus 0.460 volts. So of course that then is the E, or the E0, that you plug in to calculate the Gibbs free energy for this overall reaction right here. Okay, you plug that into the delta G is equal to negative NF E0. That's how that works. Okay. So that's my stopping point. I kind of wanted to stop there so we can get a running start at an example first thing on Friday.